Today I'll be presenting on wind resistance building design towards saving lives and property, done by myself, George Carl. Introduction. Wind can be defined as a movement of air, the full nature of which is not fully understood. But two major contributory factors that can be given are: firstly, convection currents caused by air being warmed at Earth's surface, becoming less dense, rising and being replaced by colder air. 2. Transference of air between high and low pressure areas. The physical nature of the ground or topography over which the wind passes will have an effect on local wind speed, because obstructions such as trees and buildings can set up local disturbances by forcing the wind to move around the sides of the obstruction or funnel between adjacent buildings. In this picture, it is showing a plan view of a building and the different elevations of the building. It is showing how pressure on windward face, suction and acceleration around ends, and large eddy exerting suction on near face. On this elevation, it is showing how the roof is pitch roof or less than 30 degree. Roofs over 35 pitch usually develop positive pressure on windward slope with suction over ridge, and on less slope, wind in direction of ridge will create areas of suction along all wind edges. Wind pressure can be negative when it creates a pulling force and positive when it creates a pushing force. Suction or negative wind pressure is defined as the means by which matter is drawn from one space into another, because the pressure inside the second space is lower than the pressure in the first. In low buildings, pressure on windward face with vertex create near ground level and surface around end walls. Wind striking on exterior walls exerts a positive pressure on the wall, which forces air through openings and into the interior of the building. At the same time, the windward wall is received positive pressure. The side and rear walls are receiving negative suction pressure. Therefore, air within the building is being pulled at an opening in these other walls. Low and high buildings. Suction over flat roof. When a building is pressurized, the internal pressure pushes up on the roof. This push from below the roof is combined with the suction above the roof, resulting in increased wind load on the roof. The internal pressure also pushes on the side and rear walls. Therefore, a pressure building increases the wind load on the side and rear walls as well as on the roof. Aerodynamic pressure. The interaction between the wind and the building. The highest uplift load occurs at the roof corners. The roof perimeter has a somewhat lower load, followed by the field of the roof. Exterior walls typically have lower loads than the field of the roof. The end of the walls have higher suction loads than the portion of wall between the ends. However, when the wall is loaded with positive pressure, the entire wall is uniformly loaded. The negative values, that is acting upward from the roof surface and upward from the wall surface. Positive values indicate positive pressure acting inward on wall surfaces. Aerodynamic influences are accounted for by use of external pressure coefficients, which are used in load calculations. Now we'll be talking about the factors that should be taken into account before the magnitude and direction of wind pressure can be determined. These include the height to width ratio of the building, the length to width ratio of the building, the plan shape of the building, the approach topography exposure of the building, and the proximity of surrounding structures. Account must also be taken off on unlikely openings in the building because the entry of wind will exert a positive pressure on any walls or ceiling encountered. This internal pressure must be added to or subtracted from a type of pressure. The length to wind ratio of the building. All buildings are at some time subjected to wind pressure, but some are more variable than others because of their shape, exposure, or method construction. One method of providing adequate resistance to wind pressure is to use material of high density. Therefore, that buildings that are clad with lightweight coverings are more susceptible to wind damage than those using the heavier. The approach topography exposure of the building. To overcome the problem of uplift or suction or roofs caused by negative wind pressure, adequate fixing or anchorage of the lightweight coverings to the structure frame is recommended. This can be achieved by the quality or holding power of the fixing used, or by the number of fixing employed, or by a combination of both. Now, when designing an office building, designers should consider the following. Although each area of the country has a predominant prevailing wind, buildings requiring wind bracing are usually treated the same at all likely vulnerable positions to, to counteract changes in wind direction and the effect of local eddies. Therefore, when planning site layouts, plan positioning, erection of scaffolds, and holding if safe working conditions are to be obtained on building sites. So when designing an office building, designers should consider the following. Regular winds. In many locations, wind with low to moderate speeds occur daily. Damage is not expected to occur during these events. Secondly, stronger winds. At a given site, stronger winds, example, wind with a basic wind speed in the range of 70 to 80 miles per hour peak gust, may occur from several times a year to only once a year or less frequently. So, wind that is 70 to 80 miles per hour is the threshold at which damage normally begins to occur to building elements that have limited wind resistance due to problems associated with inadequate design, strength application, or material deterioration. Thirdly, design level winds. Office buildings that experience design level events and events that are somewhat in excess of design level should experience little, if any, damage. However, design level storms frequently cause extensive building envelope damage. So structural buildings also occurs, but less often. Damage experienced with design level event is typically associated with inadequate design. The exceptions are wind-driven water infiltration and windborne debris damages. Furthermore, details of the effects and assessment of wind loads on buildings should be produced on a general method of basic construction. Now, evaluating office buildings for risks from high winds. To evaluate risk for windstorms, the following steps are recommended. Firstly, determine the basic wind speed. As the basic wind speed increases beyond 90 miles per hour, the risk of damage increases, and it continues to increase as the speed increases. So therefore, to compensate for the increased risk of damage, design, construction, and maintenance enhancements are recommended. For buildings not located in hurricane-prone regions, determine if the building will be used for emergency response after a storm. Example, temporary housing, food or clothing distribution. So, if so, refer to the design, construction, and maintenance enhancement recommended for office building in hurricane-prone regions. Thirdly, for office buildings in hurricane-prone regions, determine if the office building will be used for a hurricane shelter and or for emergency response after a storm. If so, refer to the design, construction, and maintenance enhancement recommendation. Now, we'll be talking about the steps that should be taken when designing and building. Step 1. Before that, when designing and building, good wind performance depends on good design, including detailing and specifying material, application, maintenance, and reply. A significant shortage of any of these five elements could jeopardize the performance of a well-built design against wind. So therefore, step 1. Calculate loads. Calculate loads on the main wind force resisting system. The primary structural elements such as beam, column, shear walls, and there are clamps that provide support and stability of the overall building. In the past, architects seldom perform load calculation on the building envelope for roof and wall coverings, door windows and skylights, and rooftop equipment. Neither did their structural or mechanical engineer, in large part as a result of not determining loads on these elements and designing them with adequate load resistance. Building envelope and rooftop equipment failures have been the leading cause of failure during past wind events. 2. Step 2. Determine load resistance. After loads have been determined, it is necessary to determine a reasonable safety factor when using allowable stress design or a reasonable load factor. A minimum safety factor of 2 is recommended, unless an important factor that is required shall be used. A minimum safety factor of 3 is recommended for anchorage of exterior mounting mechanical, electrical, and communication equipment. For structural members and many cladding elements, load resistance can be determined by calculations based on test data. Detailed design. Design, detail, and specify the structural system, building envelope, and exterior mounting mechanical, electrical, and communication equipment to meet the factor design loads based on appropriate analytical or test method. As part of a detailed design effort, load path continuity should be clearly indicated in a contract document. Load paths need to accommodate design uplift, braking, and overturning loads. Load paths continuity obviously applies to elements, but it also applies to the building envelope elements. Step 4. Durability. Because some locales have been aggressive atmospheric corrosion, such as building located near oceans, special attention needs to be given to specification of adequate protection for fresh metal or specify alternative metals such as stainless steel. In some locales, termites present a significant threat to building performance. Where termites are problematic, it is recommended that the soil is treated with a termiticide applied by a professional company experienced in termite treatment. It is also recommended that if wood or wood-based products are specified, they should be preservative treated. Also specify that surfaces that are cut or drilled after treatment are to be field protected with a suitable preservative applied in accordance with the manufacturer's recommendations. Lastly, wind penetration. Although prevention of building collapse and major buildings damage is the primary goal of wind resistant design, consideration should also be given to minimizing water damage and subsequent development of walls from penetration of wind-driven rain. With this approach, it is assumed that some water infiltration will occur. The water is intercepted in an air pressure equalized cavity that provide drainage from the cavity to the outer surface of the building. So therefore, in conjunction with the rain screen principle, it is desirable to avoid using sealant as a first line of edge against water infiltration. When sealant joints are exposed, obtaining long-lasting watertight performance is difficult because of the complexities of sealant joint design and application. So now I'll be showing a video on the material that is being used to withstand hurricanes.
There's a building material that can keep houses intact during hurricanes, earthquakes, tornadoes, and fires. It's been widely used around the world, but the US lags behind in adopting the construction technique. That's about to change.
Housing economists will tell you that 77% of homes built in the United States are at extreme risk for some type of natural disaster. The East Coast is primarily hurricane. The Midwest is tornadoes, which we will also survive. The Rockies and the West are wildfire plus seismic events. We're resistant to all of that.
There was a record $300 billion in disaster damages in the US in 2017, with devastating fires in the West and hurricanes in the East. Ken Gallagher is the CEO of RSG 3D, one company that wants to help. It's bringing a building material known as a 3D cementitious sandwich panel to the masses in the US. Each panel consists of fire-retardant foam sandwiched between two wire mesh faces. The two faces are connected with reinforcement wires that run through the foam, and the whole thing is enveloped in concrete. It's very strong if built properly and can withstand high winds, earthquakes, and even fires.
A wood structure will combust almost immediately, and studies show that once a wood structure has 4 or 5% of the building on fire, it becomes a total loss because there's no stopping the fire. There's no place for a fire in a 3D panel building to start because you've got a concrete exterior and nothing is combustible within the materials.
The technology is not new. NASA has been using a version of it to build spacecraft for years because of its strength, and former President Carter used the material in the US for rehabilitation efforts decades ago.
One of the major push for that technology actually was the adoption of that system by our former President Carter, where he used that in rebuilding some of the damaged building that happens in Florida and other places like Georgia and so forth through his Habitat Charity Foundation.
Habitat for Humanity built with the panel back in the early 1990s and survived Hurricane Andrew without a scratch.
Carter's use of the sandwich panel drew attention to the technology, but it was not clear at the time how to manufacture it on a large scale. But a company in Austria called EVG cracked the code and created machines to assemble the panels, bringing down the cost of manufacturing. RSG 3D is one of a handful of companies using EVG's technology to bring the material to the States for mass production. Now, higher lumber costs, expensive skilled labor, and more demanding building codes are making it an appealing alternative to conventional construction.
The reason the product has not been used well in the United States to date is because we have wood. The United States is blessed with multiple forests, and wood was an inexpensive building material up until the last 5 years. With the new energy code, especially up in the northern states and in California, they want net zero houses. You cannot get to a net zero house construction with wood.
The panels are already in homes all over the world, but experts say that more education and updated building codes are needed for this to go mainstream in America.
The initial cost, if the engineer does not know how to use it, it's going to be expensive. So it's not the materials, it's not the system, it's the familiarity of the engineer of what is this system can do.
When used properly, Gallagher says the cost of using these panels is the same or slightly cheaper than conventional building methods.
We have to change the entire dynamic of how we want to build product in the United States, and it's going to have to be this type of technology because it's available, it's effective, it's efficient, and it gives you a much superior product at the end of the day. So we're not going to have any other choices. This is where the industry is going.
thank you guys, and that's the end of my presentation.